So I'm just going to go ahead and start a new page here. So essentially what we had in the last important thing that we had was Q of t is equal to C1 e, some constant, times e to the negative 800 t plus C2 e to the negative 3200 t plus our particular solution 3.75 times 10 to the negative fourth. So from here, we now have an equation of the actual charge. And in the original problem, we were told that the initial energy stored in the circuit is 0. What does this mean? This actually gives us some sort of initial condition. It actually gives us an initial condition that Q of 0, so Q at time 0, is equal to 0, since there's no initial energy stored, which essentially implies that the current at time 0 has to be 0, since I of t is equal to dq over dt. So what does this mean? This means that we now have some sort of initial condition for our equation here. So using this first one, q of 0 is equal to 0, we can set each of the t values equal to 0 and q of t equal to 0 and actually get some sort of value for C1 and C2. So I'm just going to say 0 equals C1 e to the 0 is just 1, so times 1, plus C2 times e to the 0 again is just 1, plus 3.75 times 10 to the negative 4. So then we have the equations just equal to C1 plus C2 equals negative 3.75 times 10 to the negative fourth. And we'll just call this like equation 1. Then we're going to use our second initial condition, I of t. I of 0 is equal to 0. So I of t is equal to the time derivative of q of t. So we just have to derive this whole equation and define I. So I of t is equal to dq of t, which we have the equation for, over dt. So that's just going to be negative 800 c1 e to the negative 800 t minus 3200 c2 e to the negative 3200 t. Right? It's just really simple derivatives of e. And it's plus 0, of course, since this is just a constant, so that's just plus 0. And then we can actually use the initial condition. I of 0 is equal to 0, so that's equal to negative 800 C1, again times 1, minus 3200 C2 e to the 0 is 1, so it's going to be times 1. So our second equation is just negative 800 C1 minus 3200 C2 is equal to 0. I'll call that equation 2. So you can either use matrices or substitution to solve these. I think matrices is the easiest way. I just call my coefficient matrix, just call it A, is equal to, we'll just take the first equation first, 1, 1, so this is C1, the coefficient of C1, coefficient of C2, and then for our second equation, the coefficient of C1 is negative 800, and the coefficient of C2 is negative 3200. So then the right-hand side matrix, or the answer vector, is just equal to negative 3.75 times 10 to the negative fourth for the first equation. And then for a second equation, it's just 0. So to find the c vector, which is just equal to c1, c2, the c vector is just going to be equal to the inverse coefficient matrix times the right-hand side vector. And I'll do this on another page. So if you do it in your calculator, you can just find that the c vector is equal to negative 5 times 10 to the negative fourth, and then 1.25 times 10 to the negative fourth as well, which implies that, well, C1 is equal to negative 5 times 10 to the negative fourth, and C2 is equal to 1.25 times 10 to the negative fourth. And we can actually use these in our original charge equation. So now we can say that Q of t, now we have actual values for C1 and C2, is equal to negative 5 times 10 to the negative fourth. I'm just going to plug in everything. E to the negative 800 t plus 1.25 times 10 to the negative fourth times e to the negative 3200 t plus our 3.75 times 10 to the negative fourth. So here's our full equation for the charge. But we're not really done with this problem yet because it was initially asking for V naught T, which is a voltage across a capacitor. And we know that the voltage across any capacitor is just equal to the charge, we'll just say of time t, over the capacitance. So we have Q of t, and we know what the capacitance is, and we can just make a substitution here. So 1 over the capacitance is just 1 over, from the very original slide, it was 6.25 times 10 to the negative 6, and then just times our entire Q of t equation that we have above. So this is actually just equal to 16 times 10 to the fourth Q of t, which if you multiply everything out, just multiply this 16 times 10 to the fourth by this coefficient, and this number. You'll just find that V naught of t is equal to 60 minus 80 e to the negative 800 t plus 20 e to the negative 3200 t. And there's your voltage across a capacitor at any time t.